So we've got this massive mathematical function with billions of dials, and we said training is the process of turning those dials until the model gets good at predicting the next word. But think about that for a second. You've got 175 billion dials. Each one can be turned by any tiny amount in either direction. How on earth do you figure out which ones to turn and by how much? You can't try every possible combination. There are more combinations than there are atoms in the universe. You can't do it by hand. No human could make sense of 175 billion numbers. So how does it work? Here is an analogy I borrowed from 3 Blue 1 Brown, which resonates very well. Imagine you're standing in a vast hilly landscape. Mountains, valleys, ridges, slopes, stretching out in every direction as far as you can see. And your job is to find the lowest point, the deepest valley. But here's the catch, you're blindfolded. You can't see anything. You can't look around and spot the valley. All you can do is feel the ground under your feet. You can feel which direction slopes downhill, and you can take one small step in that direction. So that's what you do. You feel the slope. You take a step downhill. You feel the slope again. Take another step downhill. And you keep doing that, step after step after step, slowly making your way lower and lower. Now, every part of this analogy maps directly to the real thing. Let me walk you through it. Let's start with the landscape itself. What is this landscape? Each point on the landscape represents one possible setting of all 175 billion dials. One particular configuration of the model. There are an unimaginable number of possible configurations. That's why the landscape stretches out in every direction. And the height at any point, that's how wrong the model is with those particular dial settings. The higher you are, the worse the model is at predicting the next word. The lower you are, the better. This height has a name. It's called the cost function, or sometimes the loss function. It's just a single number that measures, across all the training examples you've shown the model, how far off were its predictions. So at the very beginning of training, when all the dials are set randomly, you're standing somewhere high up on a mountaintop. The cost is enormous. The model's predictions are garbage. It's guessing purple when the answer is matte. The goal, find a valley. Find a setting of those dials where the cost is low, where the model actually makes good predictions. And you do that the only way you can when you're blindfolded, feel the slope, step downhill, repeat. Now, what does feeling the slope actually mean in practice? Well, remember, the model is like a massive factory. Data flows in one end, passes through billions of dials, and a prediction comes out the other end. Now, say the prediction is wrong. The model predicted purple when the answer was matte. You need to figure out which dials to adjust. But there are 175 billion of them. You can't just try each one individually and see what happens. So, instead, you work backwards. And the reason you can work backwards is the key insight that makes all of this possible. Here's the thing about this factory. Every single station on the assembly line does something simple and well understood. One station multiplies two numbers, another adds a few numbers together, another applies a simple squishing function. That's it. Each individual operation is basic math. Stuff you could do on a calculator. And because each operation is simple, every station can answer one easy question about itself. If my input wiggles a tiny bit, how much does my output wiggle? That number, how much output wiggle you get per unit of input wiggle, is the station's sensitivity. And here's the nice part. Because the operation is so simple, the station already knows its sensitivity for free. It doesn't have to test anything. Let me make that concrete because it sounds abstract until you see real numbers. Picture the simplest possible factory. One dial, call its value 5. It feeds into a station that doubles its input, so 5 becomes 10. That feeds into a second station that multiplies by 3, so 10 becomes 30. And let's say the right answer was 24. So our output of 30 is too high by 6. That's our error. Now the question we actually care about. If I nudge that dial up a little, does the error get better or worse? And by how much? Watch how each station answers locally. The times 3 station wiggle its input and the output wiggles 3 times as much. Its sensitivity is 3. The doubling station wiggle its input, output wiggles twice as much. Its sensitivity is 2. And here's the key insight, the thing that makes the whole method work. To find out how much the dial affects the final error, you just multiply the sensitivities along the path. 2, then 3, so 2 times 3 is 6. A tiny nudge to that dial gets amplified by 2, then by 3, landing as a change of 6 at the error. So if I bump the dial up by a hair, the error goes up by 6 times that hair. The error gets worse, which immediately tells me the right move is to push that dial down. And you can check this isn't a trick. Nudge the dial from 5 up to 5.01. Run it through. 5.01 doubled is 10.04 times 3 is 30.12. The error went from 6 to 6.12, up by exactly 6 times the nudge. The number we computed predicted the real change perfectly without us having to run any experiment. That is the chain rule. The effect of a dial deep inside the factory on the final error is just the product of the simple local sensitivities along the path from that dial to the output. Each piece is trivial, multiplying them is trivial, and that gives you the whole thing. So, backpropagation just walks backwards through the factory, station by station, multiplying these local sensitivities as it goes. By the time it reaches the beginning, it has worked out in a single backward pass exactly how much every dial pushed the final answer up or down. Not by testing 175 billion dials one at a time, just by multiplying simple numbers backward through the chain. The result is a set of tiny instructions, technically called the gradient, that says for every single dial, turn it up a little, turn it down a little, or leave it alone. Turn this one up by a hair, turn that one down by a hair, leave this one alone. For all 175 billion dials simultaneously, that's one step downhill. Then you show the model another training example. It makes a prediction. You measure the error, you calculate the gradient again, you adjust all the dials again, a tiny amount. And you do this over and over, billions and billions of times. Each time the model gets a little bit less wrong. The cost goes down a little bit. It takes one more step downhill. This whole process, feeling the slope, stepping downhill, repeating, has a name. Gradient descent. That's literally how the model learns. Now, the skill here matters a lot. This isn't something that happens on your laptop. Training a frontier LLM requires tens of thousands of specialized chips, GPUs, running in parallel 24 hours a day for months. The electricity bill alone can run into tens of millions of dollars. 3 Blue 1 Brown pointed out that if you tried to do the computation for training a large model at a rate of 1 billion operations per second, which sounds fast, it would take you well over 100 million years. That's the kind of scale we are talking about. The only reason this is possible at all is because these GPU chips can do trillions of operations per second and you run thousands of them at the same time. So here's what I really want you to take away from this section. No human being designed the knowledge inside these models. Nobody decided what facts it should know. Nobody wrote rules for grammar or logic or reasoning. Nobody looked at 175 billion dials and said, yes, this particular dial should be set to exactly this value. What humans designed was the process, the game, the landscape, the method of walking downhill. And then they let the model sculpt itself through trial and error at a scale that is genuinely hard to comprehend. Billions of tiny adjustments across trillions of training examples repeated over months of compute. And at the end of that process, what comes out is a function that can predict the next word well enough to hold a conversation, write an essay, or explain a concept. Nobody fully understands why those specific 175 billion numbers work, but they do. So now we know the raw ingredients, we know what the model is, and we know how it learns. And what it's learning to do is predict the next word. That's the whole game. But here's what might be bugging you. Predicting the next word sounds simple, almost too simple. If I give you the sentence, I went to the blank, you could guess store or park or doctor. That's not magic. A 5-year-old can do that. So why are these models so shockingly good? Why can they write essays and explain quantum physics and debug code if all they're doing is predicting the next word? The answer is context. A next word predictor without context is just a glorified autocomplete. But a next word predictor that deeply understands everything that came before, every word, every relationship, every subtle implication in the entire text, that is something else entirely. That is what makes this so powerful. Now, earlier architectures, things like RNNs and LSTMs, did use context. They weren't blind, but they struggled with long-range context. They'd pass information, word by word, like a game of telephone, and by the time you were 500 words in, the meaning from the beginning had faded. They could see nearby words clearly, but the distant ones were a blur. What changed everything was an architecture that could look at every word in the text directly, no matter how far away. No telephone game, no fading, every word can reach out to every other word all at once. That architecture is called the transformer, and it's what made context understanding so deep and so effective that next word prediction went from useful to extraordinary. That's what we're looking at next.